introduce Forrest. We'll be talking today about some OSINT stuff, which is really awesome. Jordan and I tried to OSINT him, which, we're not as effective at it, but we found some interesting things. So as opposed to bringing them all up right now, I think we're going to pass it on over to Forrest, and he's going to tell you about some pretty awesome stuff. Forrest, have at it, and we hope you're with us next year as well.
Thanks, guys.
Thanks, sir.
So welcome to Jeepers Creepers. This is all about scope creeping really hard using advanced OSINT. We're going to use MongoDB, Node.js, and VivaGraph to visualize scope at scale and also just mine data sets at scale. So I'm going to do a brief intro of myself. We're going to talk about our overall goals and what they should be when we're doing OSINT. We're going to talk about how we scale OSINT effectively, especially using visualization in order to track all the data points that we collect. And then we'll move on to kind of part two of the talk is talking about just getting open source data ourselves and building our own OSINT APIs to be more effective as pen testers. So my name is Forrest. I'm a CPA turned pen tester. So I actually went to school for accounting and then didn't do any accounting. I've just been full-time pen testing for going on 6 years now. I'm a manager at Clifton Larson Allen. I manage a team of pen testers. I love Vim. I still write a lot of my tools in Vim. Not a huge fan of dark theme, which I feel like is different than a lot of my coworkers. So you guys are going to see a lot of light theme slides in this presentation. I have a growing love for offensive JavaScript, which should become apparent throughout the talk. And when I'm not hacking, I just like to get outside. I love rock climbing, biking, and swimming, and just getting outside. So with that, when we're performing OSINT, our goals should be to truly know our target. So we're going to go out and collect a bunch of data points, and then we have to string them together to actually understand what it is we are attacking. So we can do that with deductive logic or inductive logic. The deductive stuff is a little bit more straightforward or boring. So this would be, we see that this in-scope IP has a reverse entry with this host name, therefore that host name's in scope. Pretty straightforward one-to-one correlations there. It's in inductive logic where you can start to make more broad assumptions about your target based on what you're seeing. So first you have to observe a pattern, and you have to do that by connecting data points that you've collected about your target, and then understand what that pattern is telling you or make inferences about it. So this would be like if you have a bunch of in-scope domains and some of them have one name server and others have another name server, you might be able to deduce that either they're hosted by different providers, they might be managed by different people, they might even have a different geographic location. And so by seeing those patterns, you can start to understand your target a little bit deeper, and then you can take those inferences that you've made and use deductive logic in order to confirm or deny them. So the usual way that we used to do OSINT would just be use some of these tools, go out and collect as much data points as we could, go through those data points, manually see which ones look interesting, and then maybe do some recursive searching and dig a little bit further on the interesting stuff that comes out. So the problem with this approach is that a lot of these tools are just command line tools that output flat lists, so you get these like silos of data, and they're just data points. So there's not much really like context to the data other than the tool that it came from. That recursive searching is usually very manual, so you might have output from one tool that you want to use as the input for another tool, and you have to wait for tool A to finish before you run tool B on the data set that tool A spit out. So that would be the synchronous workflow that really slows things down. So either it's very manual to actually grow your understanding of a large organization, or you take the automatic approach, you just try to automate everything and have your tool go down every rabbit hole and get you tons and tons of data, in which case you'll oftentimes just get a bunch of irrelevant data and you have to spend a bunch of time sifting through and weeding out the bad stuff. And oftentimes that approach just gives you those deductive inferences, those one-to-one correlations. So in order to understand our targets a little bit better, what we want to do is start to look at the intersection of different data sets that we've collected. So here's some in-scope domains, some in-scope IPs. I think this is a good point to pause and note that in a lot of these examples, I'm going to be using my employer as the data set that we are trying to target here. They are a large organization, so it's very fitting. So in this case, we have a bunch of in-scope domains, a bunch of in-scope IPs, and we see that at the intersection of those two data sets, we have some understanding of those two data sets, and we get to see a connection here between them and understand that data a little bit better. So whether this was a reverse DNS record or a forward DNS record, or we just looked it up on Shodan, we know that this domain is associated with these IP addresses just by looking at it. So what's key to note here is that we can represent those intersections of large data sets just by these edges on a graph. So if we add another data set to layer in here, which would be subdomains, we start to see patterns emerge that we can start to make those inductive inferences about our target here. So same data set, we've just added in some subdomains. And again, you wouldn't really be able to show this effectively in a Venn diagram with like 3 circles. It would need like sort of a 3-dimensional Venn diagram to show all these relations at once. But just know that all of these edges in this graph are the intersection of data. So with this, we see that, like our target has like a main domain over there on the left with a bunch of subdomains. We have a bunch of in-scope domains that are associated with just these 2 IP addresses over on the right. We might start to infer that either these are docked or they're all displaying the exact same like web interface for their @ record. They don't really have a bunch of subdomains, so I'm thinking they're more likely to be docked. And if we add another layer to this, so just name servers, these green dots, we start to see even more patterns emerging. So for example, there's this bankers advisory domain that was grouped over with the stuff that we'll assume is maybe docked, but it's hanging out closer to our main domain now because we see it has the same name servers. So maybe it was previously docked and now it's been adopted by the same people that are managing the main site, or they have started to use that domain a lot more. So maybe it's a juicier target than some of those other in-scope domains. So graphing Recon is not a new concept. So I was heavily inspired by Bloodhound and their ability to graph Recon for internal purposes when you've gotten on an Active Directory domain. And so, I was wondering what kind of insights we might be able to pull out of our external Recon by using graphing. There are some existing tools that spit out OSINT graphs. So this is DNS Dumpster. It's kind of in that approach of automate everything. You just give it a target. It goes and tries to find everything it can in DNS about that target and subdomains, and it can present it in a graph, but you can't really recurse through it. There's Maltego, which is designed for OSINT, and it's, here's an example of some DNS records, mapping out to IPs, ranges, some people, their usernames and Twitter accounts. But a lot of these transforms are kind of one at a time and directional transforms. Maltego is not cheap. I might mention it's not open source. There is Spiderfoot. It's an existing Recon tool that is also in the automate everything camp. You give it a target, it tries to go down every rabbit hole, every avenue, find every data point that it can about your original target. And it has some graphing capabilities, but in my experience, you have to spend a lot of time kind of weeding out the irrelevant data. So why reinvent the wheel if we have existing graphing tools for OSINT? First, I feel like open source intelligence gathering should be done with free and open source tools. So that should be good enough, but if not, also we can eliminate synchronous workflows so we can speed things up. That manual recursive searching can be really tedious in other tools, especially when you're talking about large targets. We also want to make sure that our graphs are as flexible as possible. So I don't feel like directional structure in OSINT graphs really makes sense. It doesn't really matter if we found out, an A record or like a host name maps to an IP, we don't need to know if it was an A record, quad A record, reverse lookup, a brute force, Shodan. That connection means the same thing in all of these cases. So trying to put that additional structure to the graph doesn't really make sense. It can also prevent us from seeing patterns that could be useful. And then a lot of these other tools, when you're doing transforms, you're just looking for a particular type of data from a search that you did on a node. And so a lot of times, even though there might be metadata available, for example, if you're doing whois lookup, your transform might only give you some subset of the data that might be useful to you out of that search. So we want to keep the metadata as much as possible. So to graph our own OSINT, we need a graphing library. I went with VivaGraph.js because it was designed to be the very fastest JavaScript graphing library, and they succeeded. They also have customizable nodes. So this graph here on the slide is just of the contributors. And so the nodes are, they have custom pictures. I like being able to represent different data types with different images. Also, you can customize the physics, so you can modify the spring length or how quickly the graph renders, which can be useful. It's also very easy to get started. So a very modular library, very simple to start graphing things. And it's great for large graphs. So for instance, this is a graph of all of Reddit, where all the links between the nodes are subreddits, and it is searchable. So all these highlighted nodes here are relevant to this search term programming. So our graphs are not going to be that big, so this library should be perfect. So in order to start graphing, it's very simple. You create a graph object. You just assign some attributes to your nodes and how they're going to be displayed. Then you apply some physics to the graph. This is just the default physics. Comes with some examples in the tool set. Then you start rendering the graph so that even though it's an empty graph, as you add nodes, it will start to animate those nodes as they're added. And then you have a graph object that we'll call myGraph going forward that you can work with. So here, I've just written a little helper function in order to add nodes and links. We're going to assume that pretty much after our seed node, the node that starts the whole OSINT process, all other nodes are going to be the result of a query that we ran on a node that's already on the graph, or its parent node. So we've just got a little bit of logic to make sure, like a sanity check, that we're not trying to add an undefined node. Some of the APIs that I wanted to use were returning undefined nodes in some instances. So a little sanity check there. Also make sure that the node's ID, which is the actual data point that we're collecting, is not blank, to make sure we don't have a bunch of blank data on our graph. And then if those sanity checks pass, then we just use a couple of built-in functions in the library, add node and add link, to put the node on the graph and then link it to the parent. So every node has an ID, which is the data point. It has a type, which is how it's going to be displayed on the graph. And then it has a parent, which is the node that we search in order to get the new node. So once we have that helper function, we can start to graph things. We have to keep in mind a few other design requirements. So we're going to keep non-directional graph links to make sure the graph is as flexible as possible. We want to make sure that we keep as much metadata as we can to link second and third connections. We want to be able to search our nodes and use regex to do very refined searches on a large data set. We want to make sure that we keep our actions asynchronous at all times if possible. So this has the added benefit of being able to work with nodes as they're actually hitting the graph. So you don't have to wait for this search to finish before you can start to look into its results. We're going to use Node.js because it is asynchronous by nature. And then we'll use WebSockets as kind of a trick in order to create an asynchronous flow of data between the client and the server. So the way that I like to describe this is as like a kitchen in a restaurant. So the restaurant would be like our client side, where we have a bunch of nodes on our graph. They can all be, we can run searches on a lot of them. Those searches are like orders to the kitchen, which is our server side. And our server side can be working on a bunch of different orders at a time. And as each one finishes, it can be sending it back to the client side. So in this example, the window of our kitchen between the restaurant and the server is WebSockets. So WebSockets allows you to send data directly from a web server to a client without the client opening up a connection to the web server. So it replaces the long polling technique where, traditionally, if you were trying to get data client side with Ajax, you would open up a connection to the server, and then you have to wait for the server's response in order to present that data and then close the connection. So here, we're just using small JSON objects and just passing a JSON object that represents a search to the server. The server works on it, and then it can just prompt the client to display a JSON object that represents a node when it's done. So this keeps everything totally asynchronous. Client side, here's just an example of if we were going to run a brute forcing module going through the Alexa list on a domain, that would be triggered client side with some code like this, where we check to see what's the node that's currently selected. And then we'll just emit an event on the socket with the server that says brute force subdomains, and it passes the selected node as an argument. On the server side, it's always listening for that event on the socket. So if it hears that event, brute force subdomains, it looks at the query, it runs a quick check and searches a non-valid domain to make sure that we don't bump up against a wildcard entry. And then we just loop through the Alexa list. And if we have a valid result come back, we create a node object. Again, it's just an ID, which is the data point itself, a parent where it's going to be connected back on the graph, and then how it's going to be displayed. What type of node is it? So in this case, as we find valid entries, we just create those JSON objects and then emit an event back to the client called add node. Client side, very simple. We're always listening for that add node event. And whenever we receive it with the node itself as a parameter, we call that helper function to put it on the graph. So very simple architecture. This is what it looks like when you string that all together. So again, we're going to use CLA Connect as our target. So we can be doing, simple transforms, IP address, mail server, name server, that sort of thing. We've got key bindings for these things. So if a lot's happening, I'm just typing. We can start brute forcing subdomains. So we'll assume that this could take, a minute or so to finish. But while it's doing that, we can also be looking up subdomains with like attacker target. And we can be paring down results that don't make sense for us. So like NX domain basically means that these subs don't really have an IP associated with them, so we can remove them from the graph. We're still brute forcing behind the scenes, but again, we can be running transforms on these at the same time, so we can work with the data as it's coming in. We can also start to look for specific things, so we can do some port scanning. And again, we want to do this at scale. We want to do this in mass. So we can just trigger a port scan that's happening on all IP addresses at the same time. We can then select those nodes that have port 80 open. That's what we're interested in. And then we can, start to look into what are these services? What are these things that have something with port 80 open, right? And go through the list pretty quickly. Oh, type abuse. That's fine. So in this way, we can quickly scale up and scale down our graph based on search terms that we're interested in. This is not just useful for mining data about systems. So just another example, this is a Shodan query that I just ran on this IP. And then we can do the recursive searching very quickly. So I see it's associated with this organization, and I just Shodan queried that organization, and we get a bunch of free data and open ports and all that stuff. So then we could look for what we're interested in, pare down the graph again, and check out the interesting nodes, or look for interesting patterns, which we'll talk about in a minute. We can also use this technique in order to mine other data sources, like learning about employees. So for instance, we can mine LinkedIn. We just need the org ID in order to get started. We'll tell it, a number of pages to mine. And right now it's opening up a headless browser in order to mine this data. So it might take a minute on this first one. While it's doing that, there we go. While it's mining those pages that we told it to, we can also be pulling in more data on employees if that's what we want. So we can, for instance, do a search on Hunter.io and get a bunch more emails. And the LinkedIn results are still flowing in. We can also do transforms again on a large number of nodes at a time in order to generate emails for the data points that we got from LinkedIn. So if we know the email convention, which we should with this sample here, then we can generate email addresses for everyone from LinkedIn. We can also just search for interesting targets, delete everything else, and bring back what we want to look at. So again, we can bring back information that's pertinent to what we're searching for in these large data sets. You can also export graphs and then import them back in order to look for different things. So you can just grow the graph as big as you can and then search for different subsets after that. So some interesting patterns that we've seen in the past. Here's an example where we have a very long SPF record. The pattern that we saw right away was that some of the domains that are listed have name servers associated with them, but this one does not have a name server associated with it. So we were able to infer that this domain was actually available for purchase, and purchase the domain, create our own DNS records, and then perfectly spoof our target during a phishing campaign. So we've seen this quite a few times, just neglected entries in SPF records. Here is a graph of a simple WWHF search. So if this was our target and we ran a WWHF search, WWHF identified that at least one other domain that is similar in name also has the exact same WhoisGuard email address. So then if we run a recursive search and actually search WWHF for this email address as the main contact for the domain, then we get a bunch of other domains that you might not be able to find, again, if you were just searching WWHF manually or using a command line tool to do that. You might not get that connection and understand that it's important and find all of these other in-scope domains. We also have other WhoisGuard email addresses listed here that we could recursively search those and potentially find additional in-scope targets. So here's another one where we graphed some password data breaches. So this is the dehashed API in graph form. This is a coworker of mine. He gave me permission to do this. I looked him up and found that this password that he used to use all the time was associated with at least 3 breaches. So when you see clusters like this, you can infer that this might be a password that this user likes to use for multiple different things. So in this case, that was correct, and he has not used that password in quite a while. So you can also find useful data points, again, going back to keep the metadata whenever you can. This is a subgraph of some Hunter.io results. if you keep the source of where the email came from in your Hunter.io data, then you can find these clusters where you have a single source and multiple email addresses associated with it. And it's pretty clear that, oh, that might be an employee directory. So at that point, you go there, confirm, oh, yeah, this is a directory. If I'm trying to mine emails, throwing away that metadata would have been a disservice. But by seeing that pattern, I can go directly to the source and mine the source directly for everyone's email. So this is part 2, Be Your Own Shodan, why we should be building our own OSINT APIs. So in my opinion, if a data source is open, truly open, and someone else can mine it, then we can too. Data is very cheap. You can just get your own terabyte drive and start playing with large data sets. If you're bumping up against free API limits, or even if a paid API has some sort of rate limit that you don't like, you can always just build your own. Sometimes there isn't a free or cheap API that meets your needs. I have found instances where paid APIs are not up to date or as up to date as some of the ones that we built. And then sometimes the free or cheap APIs don't really have a feature that you really want. So for example, here's an error that we get when we try to search hacker target for a simple string. So it allows you to search for domains and find information on domains, but not just simple strings. We're going to go through how you would build your own OSINT API that allows string searches to give you results like this, and more importantly, results like this. So this is data that you wouldn't really get out of other paid APIs unless they have figured out this feature themselves. So we can search for simple strings like our target without the top level domain and find that they are the subdomain for these other vendors or services, and we can understand more about the internal workings of that company just based on this data. And depending on how it's hosted and configured and the agreements between them and these providers, some of these things might even be in scope for testing. This is just an interesting example of why building your own OSINT API can be informative. So this is a graph of, I was doing some recon on a target, and I found that their main domain was a subdomain of a very sketchy looking domain. So I did a reverse lookup in our custom OSINT API and found that the same IP address was associated with a ton of sketchy looking domains and subdomains. Some of those also were associated with an SPF record. I noticed the /28 reference in that record. /28 is small enough to where I just did a ping sweep, found these nodes over here, and then again referenced our API in order to turn those into host names. And we have found their previous pen testers as well as physical location, and confirm that this wasn't an artifact from like a real phishing campaign. So if you want to go out and get your own data direct from the source, you could use ZMAP. So ZMAP is a fast single packet network scanner optimized for internet-wide network surveys. It's basically just one of the fastest network scanners available. It's free, open source. Also comes with a whole suite of other tools for fingerprinting services, doing DNS lookups, looking into certificates. These things are very powerful, and if you want to go directly to the source and mine your own data, this is the best place to start. But if you're going to mine the internet, make sure that you have the right equipment that can keep up with those tools. Some of them require special equipment. Make sure that your ISP is cool with it and that doesn't violate your terms of services, and know that port scanning and really any type of scanning on the internet could be seen as an attack, so you might get some complaints. Also keep in mind that you need to coordinate with hosting companies. You need to know the laws in your area. provide an opt-out for people that don't want to be scanned. You have to have it well documented why you're doing your scanning and collecting. And you want to make sure that you don't DOS anyone. So randomize your scanning activities as much as possible. And finally, if you're going to scan the internet, don't scan these things. I'll leave this here as a reference. But there's an easier way, luckily. So Project Sonar is a open source initiative that Rapid7 runs. They basically scan the internet all the time for us, and then they provide their data sets for free for researchers. So these are huge data sets. They are used by paid OSINT APIs to populate some of their DBs or portions of their DBs, but I haven't seen much references of how to mine this stuff yourself. So that's a portion of the reason for this talk. So to start, just go to opendata.rapid7.com, and here's all their data sets that they provide for free. There's forward and reverse DNS lookups. There's GET responses from HTTP and HTTPS. They have certificate info, UDP and TCP, port scan information for common ports. They've got a lot of historical DNS data, which can be useful. They've even got some vuln scan type stuff in the critical IO service fingerprints. These data sets are huge. They're all gzipped, and gzipped text data, these files can be like 20, 30 gigs. When you unzip them, they can be hundreds of gigs of data. They update these about once a month. So in order to make sense of these large data sets, we're going to need to index them to make them useful so that we can search them quickly. So to do that, in our example, we're going to use Mongo. First and foremost, it's free, and it was designed specifically to handle huge volumes of data and traffic. It has a very simple query language, so we can get started right away. You don't really have to define any table structure. You really just define objects that are going to be held in the database, and then you apply indexes to those objects to search them very quickly. So again, very quick and easy to prototype, and then very powerful searching capabilities built in. So when working with these data sets, try to streamline stuff as much as possible. So this is just an example of streamlining the steps of downloading the file and unzipping it. So because unzipping it can take over an hour itself, and downloading it can take half an hour to an hour, you can combine these steps by just piping curl to standard out and then piping that over to gunzip in order to get our unzipped data here, 200 gigs. So this is what the raw data looks like. It has timestamp, the name, which is the actual record itself, the type, and then what it resolved to as an IP. In order to search this stuff, we need to index it, and you have to choose the right index. I made the mistake of using a text index at first, which is actually a full text index. It worked really well for IPv6 data set, which is much smaller than the IPv4, but it did not scale at all to the IPv4. It was never going to finish. So as an alternative, there is a multi-key index, which is sort of like you create search terms like hashtags, basically, and you put them into an array in your object. And when you apply an index to that array in Mongo, it will automatically identify, oh, I'm trying to index an array. This must be a multi-key index. And it handles everything for you behind the scenes. The one caveat is that you can only apply one of these multi-keys to any particular data set. But for our purposes, that's fine. So what we need to go into Mongo looks more like this. So we need to massage these records. We'll get rid of the timestamp that we don't care about. And we'll lop up the original entry into search terms. So we'll also ignore search terms that are 4 characters or less, because if you do a search for com, net, org, club, you get it. You're just going to get a bunch of irrelevant results. So we get rid of search terms that are too small. We end up with our search terms that are meaningful. And then we always add the domain in its top level as a search term, because that's always going to yield relevant results for that exact search term. So to do that, this is the wrong way. Again, this approach worked for IPv6, where I'm trying to iterate over a file, massage all the data, and then put it into the database one at a time. The problem here is that it takes time to put each record into the database, and Node's actually able to process these entries much faster than Mongo can insert them one at a time. So again, worked on IPv6, does not scale well. A workaround that I found to work some of the time was just console logging my massage data. So after we transform the data, we just console log it, and then in the console, we're piping to a file. So I have found that this can crash the terminal sometimes, and that's because of back pressure. So again, Node is much faster at reading and processing the data than we can actually write it out to the file. So it starts queuing up data to be written to the file, and your memory just grows and grows and grows until something bad happens. So either it crashes or it just never finishes. So the best way to do this that I've found is to use streams in Node. So streams are kind of like your pipe operator in the terminal for Node. So we use a special type of stream called a transform stream, and that actually does all of our data processing. And we just stick that stream in between reading the file and writing out to an intermediate JSON file. The reason we write out to a file is because Mongo has their own tool for importing large data sets. So use Mongo import in order to pull any massive data set into Mongo. It's very efficient. It's multi-threaded, so that num insertion workers is basically the number of threads. It also gives you this nifty status bar and update so that you know how far along you are in the process. And by default, it takes in JSON as its input type. Also, make sure that you get all your data into a Mongo database before indexing. If you index before adding your records, it's going to be trying to add the records and index them at the same time, and shuffling things around and moving files and redefining bounds and all that stuff. And it takes up too much computational overhead and it'll never finish. So always import all your objects and then apply indexes, and you should be fine. Another thing that I bumped into, another issue, was while trying to import and index these massive data sets, there is a file limit, an open file limit that any terminal instance has by default. So you can see that with ulimit A, and then you can change it with ulimit N. So we just bumped that up to 1,000. The reason I was running into issues is because of the way that Mongo represents its database is just a bunch of linked files. So in order to do that indexing process, it might have to have hundreds of files open at any given time. Also ran into issues because that indexing can take hours. If your drive falls asleep while it's trying to do that, it can halt your whole process. So this is just a screenshot of Drive Alive, which comes with amphetamine. So if you're doing this on a Mac, make sure that you use something like this in order to keep that drive alive while you're trying to do the importing and exporting steps. So once you have it all in the database and indexed, the last step is just to expose your database via an API. So again, this is just an example of the simple query language that comes with Mongo. So here we're searching our forward DNS records set for our query that we're sending from the client in that terms list that we found, that multi-key index. We limit to 1,000 results to make sure that we don't just get a bunch of irrelevant results. If we tried to search something that we didn't realize was going to have over 1,000 results, we want to cap it so that the server doesn't hang trying to get us all of those results. And then we just stringify the output and send it back to the client. So this is the full API server-side code here for both forward and reverse lookups of that data set. So in practice, this is what it looks like when you actually run a search query. So here I'm searching again for just a simple string, CLA connect. We get some of those entries where it's a subdomain of some other domain, as well as the entries that are pertinent to the domain itself. We also kept that type in our records, so we could look at records for just certain types if we wanted to, and just sort those client side. And because of the way that this is structured, and because each record has a value that we could, in essence, alphabetize, we can apply an index to value and search that as well, and we get, in effect, reverse lookups. So this is just a search for 1.1.1.1, and we see a bunch of domains and subdomains that, for whatever reason, they have an A record that just points to Cloudflare's DNS resolver. So some other ideas of how you can use this exact same technique. I've built an ASN search that I was able to create it so that it searches for, you can search an IP and get its ASN and organization, and then you can search that organization, find other ASNs and ranges associated with those. So there used to be a free data set for this, and it has since been taken down. So it should be hanging out there somewhere. You should be able to search and torrent it from someone. Very useful for large organizations in particular. You could also use this technique in order to search data breaches. So basically build your own faster version of breach parse. If you throw it all in a Mongo instance and index it, you're going to be able to search those data sets much faster. If you were to go out and replicate this same technique for all of the data sets that Project Sonar publishes, then you could get something that in effect is very similar to Shodan's core functionality, but without any API limits. So again, you can search all nodes at the same time and it won't complain. And then you could also mine Whois data yourself. This is a project that I would love to get a little bit further on, actually mining Whois data, because I love Woxy, but it's pretty limited in its search functionality. So its searches are case sensitive, and I feel like it's throwing away some valuable metadata. Whois data has a lot to offer. So while we could mine this, I guess another alternative might be to reach out to the actual providers for the Whois system and get those data sets directly. Not sure how to go about that. So if anyone knows, let me know. But with that, I feel like I might have wrapped up just a little bit early, but available for questions here. And thank you so much for having me.
So one of the questions we had was actually if you could go over Woxy a little bit more and talk about Woxy and how you've implemented that and kind of give us a background on that.
Yeah, so Woxy, I like to think of it as like a reverse Whois lookup. So, you can do a Whois lookup on an IP or a domain name, but you can't really like search Whois the way that it was scoped or spec'd. You can't search it for email addresses and that sort of thing. So you guys seeing this just fine? Here is, an example Woxy search. We've just got a Woxy API key here in the tool set. It's very cheap. So I bought, I think, 2,500 searches about this time last year. I spent them like they're pennies, and I still have like 1,800. And for 2,500, it was like $20. So it definitely goes a long way. So usually when I'm getting started trying to look at an organization and find other domains associated with it, I'm going to run a Woxy search, and I'm just going to do the keyword search. You can also do company searches, but again, it is case sensitive. So if I if I screwed up any one of the cases for any one of these letters here, it won't come back with any results, right? But you can do searches on email addresses and organizations as well. So to recurse that, we would just search for this email address that it is at our target. So we'll assume that it's the correct one. Or we'll assume that this domain, claconnect.biz, is one that they bought also. And we'll search that as an email. Did I do that right? Sorry. And we actually get 3 pages of result. So we can specify the tool set too that we actually want to. Yeah, so they own a few more.
That's awesome.
So you could do that again, and now that we know there's 3 pages of results, we can get page number 2. They have a lot.
I mean, this clearly has some implications in InfoSec and for pen testers. I'm curious if any of the BHIS testers have used this. I haven't even heard of it.
So what's cool too is if I was going to go through and search these one at a time with, again, Shodan limits you to, I think it's like a query a second, right? But by building our own OSINT API, we can query all these things for subdomains all at once. And then we can select things that just have at least one subdomain associated with them and delete everything else. Right? And then again, we can start to stick them together using name server lookups and see kind of how they're clustered or managed and what are these business units. And I know that they're all in scope, but it's these patterns that let me understand, some of these things might be acquired, some of them might be just one-off projects, that sort of thing.
Node is amazing, and that is beautiful. Holy cow. Really neat.
So
I'm going to ask another clarification question.
Yeah.
You were discussing IPv4 and IPv6, and it sounded like you were saying that as part of your investigations, IPv6 was easier to process than IPv4?
Just because the data set's so much smaller, there's so fewer forward records on the internet that point to IPv6 entries.
That was the assumption I made, and maybe I didn't hear everything, but that's also fascinating.
Another question related to that is what platform you're actually running this on. Is it on your laptop, or are you using host services, cloud services, because the data set is so large?
Oh, so I've done both. I've just had it on a terabyte drive for testing, and then what we've done is I'm actually VPN'd to our internal network, and so we've got a server that's just hosting it all the time. All in, if you go through that process to build out that custom API, your data set is it's 300 or 400 gigs. So you just need the disk space for it, and it really doesn't take that much processing. It's not memory intensive or anything like that.
Interesting. Well, one more question here, and this might be a little bit more niche, and we're thinking, given your background in OSINT, you probably know more about it than we might. At a high level, I'm going to read this verbatim. At a high level, do you consider Spiderfoot an open source equivalent replacement for paid Maltego, or as a complementary tool with overlapping and some unique use cases?
I think, well, they're definitely attempting to be a replacement, and I hope they get there. I think that's where it should go. Again, I believe that open source intelligence gathering should be done with open source tools. Spiderfoot is open source. They host a version that you can just sign up for, a free tier or a paid tier. But again, I don't like their approach in that it's give it a target and it gets everything, whether it's truly relevant or not. I like this more interactive approach of I'm going to transform on a bunch of stuff, and then I'm going to pare it down to what's relevant and then continue from there.
If folks want to find more information on this, where can they head out to?
So, yeah.
I have a softball question while you're pulling that up. Which flavor of Doritos do you prefer?
Original all the way. Well, yeah, I mean, Cool Ranch is pretty cool, but original, I would say.
Thank you for that. I appreciate
Yeah.
that.
Yeah, so you can play around with the open source version of the tool here. Again, this is just my implementation of a concept. I don't claim that I've done it the best. I think that I stumbled upon some of these architectures that work really well for OSINT. So, using VivaGraph.js is just a win out of the box. And then using WebSockets to ship your tasks back and forth. I stumbled upon that, but it works surprisingly well. So,
And allows that encrypted exchange of information. So that's nice.
yeah.
We want to get that GitHub repo in Discord. So do you want to post that or do you want to send us a link? We'd like to get that posted for people to go take a look at. And we are at the top. So Hank, let me thank you again. Welcome. Happy to have you. Thanks for speaking, all those things. We're not kicking you out quite yet, but we're almost there. Forrest, it's been a pleasure.
Hey, I can actually see you. Thanks. Thanks, guys.
Hey, it's nice to have you. Have a great morning and hang out with us. If you're not in Discord, jump in Discord too and throw some of those links in. I know we didn't get them all out there, so we definitely want. Well, salsa verde, Doritos.
Didn't know that was a thing yet. I'm gonna have to try those.
Hey, Forrest, thanks so much.
Thanks, guys.
Take care, sir.